Chinese chicken dish.
Yes.
Spicy?
Yeah.
Yeah.
But you can
Oh.
use spicy or not.
Is it Szechuan? Szechuan?
No.
No?
My favorite is
What's it called in Chinese?
Harmonic.
No, I don't know this.
Yes. Like just boiling the chicken, I think. But you add some but it's my favorite.
Nice.
I have eaten this almost 1 month, maybe.
You haven't eaten this for 1 month?
Day.
Every day? Alright, okay. You must really like it then. Okay, Ben, let's get started. So I wonder, do you think Khalifa, Gao and Summer will watch this later?
I hope so.
I hope so too. Okay, let's have a look. So, Ben,
Yes.
you're the only one here. What did you say for what's a node?
Stationary meeting point, I think. It's the way meeting something and come back and
I don't like it. I don't like it. I'll tell you what to write.
okay.
Ugh. A node in a standing wave is the point on the wave of minimum, usually 0 actually, amplitude. And then you can even draw the picture.
Oh, I can draw the picture.
Yeah, it helps. Right, the next question. Antinode. An antinode in a standing wave is the point on the wave of maximum amplitude.
I think because I did
Okay? The length of the string is 0.75 meters. What is the lowest frequency? Okay, so that is going to look like this. Bridge, bridge, and you'll have a wave like this. So that means the wavelength would be 1.5 meters. And oh, that's it. Oh, that's it.
This 1.5.
Yeah.
Lambda equal to D.
Yeah.
Yeah, that's why.
That's all. Okay. If the frequency is 800, what's the speed? Okay, so next now. V equals lambda f. Goodness, lambda f, which equals 1.5 times 800, which equals 1200. Easy peasy.
Yeah.
Easy peasy. Okay.
I can't believe the answer is correct. So.
It's crazy. All right, let's have a look now. What's the frequency of the second harmonic? Okay, it's a little bit harder. So, here is the first harmonic.
Yeah.
And then here is the second harmonic. Like that. So F. F equals V over lambda, which equals 1200 over 0.75. Right? That's 1200 over 3 times 4. 3 goes into that 4. 1600?
Sorry. I didn't see where is the 0.75.
Ah, if from here.
Oh. Is the 5? Oh, is the in the third? Oh.
They don't change the string.
Yeah. So, is the third one? Yeah.
String does not change. They kept the same string.
Oh, you mean this?
Yeah, this is still 0.75. Yeah?
So, the string is lambda.
For this one. For this this one.
I don't know this.
Second harmonic?
Okay.
You know second harmonic?
Yeah.
Yeah, okay.
Just like this.
It looks like this, yeah.
This two.
One wave.
Yeah.
Two peaks. This is half a wave.
It's
This is a full wave.
Oh, wait. So how about quarter wave?
Quarter wave? Not possible. Not possible. Because it has to be closed.
Yeah. I mean, it's close. Yeah, because when I remember, I just 1/4, half.
Not for this one. Half, 1, 1.5, 2.
Yeah.
Yeah.
So, okay. So the same speed.
Yeah, nothing.
Why? Why is the speed still the same?
I don't think the speed should be different because nothing's changed. The string is the same, the distance is the same. The only thing that's different is the lambda.
Lambda, you say is 0.7.
Yeah.
Is the same?
No, here the lambda was 1.5.
Oh, what? Yeah. So,
Yeah,
But here lambda is 0.75.
correct.
Why?
Because this is 0.75. So like, think about it like this.
Oh, so
Yeah.
it means the 0.75
Yeah.
is just halfway, like.
For the first one?
Yeah.
Yes.
So
Full way for the next one. Okay?
Yes.
Okay. A third bridge is added at 0.25. Sketch. Okay. So, we know here and here, this is still 0.75. And they put a third bridge here. And this is 0.25. So it means that this is 0.5 meters, okay? So this must be node, and the other one, oops. Come on. This must be a node. So you must have this, okay? Which means it must go like this. There must be another node here. You can't have this, because there's two different wavelengths. It must be.
And the distance side.
The distance. Each of these distances is 0.25.
Yeah.
So this is one wave here. So that means lambda is 0.5 meters. Sketch. Yep. Yeah. Yeah.
So we just draw the picture.
That's all.
Draw the picture.
Yep.
Sketch.
Yep.
Okay.
Okay. A different string of length 0.75 with no third bridge produces a fundamental frequency at the same frequency as that calculated in part 5. What is the speed? Okay, so this time, Ben, there's a new string. It's a different string. And they're saying that the V is now different.
Yeah.
The lambda is 1.5.
Yeah. It's foundation.
Fundamental.
Not much.
Yes, not foundation. 1.5. And F is also the answer for part 5.
Yeah.
What was the answer for part 5? 1600? Part 5, 1600?
Yeah, 16.
Easy peasy, easy peasy. What's the V? Yeah. Okay. Right. Are these waves, okay, are they transverse or longitudinal then?
What's that mean?
Okay. They are transverse because they vibrate perpendicular to the direction of propagation. Propagation. So they're, because this and this are perpendicular, then we call them transverse.
How about the other?
Longitudinal is when they're parallel, like this.
Oh yeah.
Good, I'm glad. See, it's good to do revision. Yeah. Okay, do you write this down? And draw the picture? Yeah? Okay. Right.
Yes, that's I think I can do this part.
Good. Let's see.
It's like a double slat.
Double slit.
Straight.
Yeah, so you've got, these are 1 meter,
Yeah.
and then they're coming out like this.
Yes.
And here you've got your fringe pattern.
Yes.
And the frequency is, what's the frequency
What's frequency?
for this one?
F.
Yeah,
1000.
1500 hertz, yeah. And the V is 330.
So
An observer, and then this distance here, 20 meters. And the question is the X.
Yeah, the X. S.
Or S, whatever, yeah, S. So S equals lambda D over D.
Yes.
Okay?
Lambda equal V over F.
Yeah.
So
330 times 20 over 1500 times 1.
I think
Cancel. 660 over 150. Cancel. 66 over 15, which is 22 over 5, which is 4.4 meters. Easy peasy?
Yes.
What happens if the D becomes 0.5?
Wait a second.
This D here,
Yeah, so
if it becomes 0.75, what happens to the S? S becomes bigger or smaller? Bigger, becomes 8.8 meters. Doubles, yeah? And if the speakers are 0.5, what is the frequency? So if you double the D, what do you need to do to the F to go back to 4.4? Well, you should make the F smaller. Yeah, you should make it 750 hertz. Oh, no, sorry. Bigger, sorry, 3000 hertz.
Yes.
Thank you. Okay, 3000 hertz.
Just I seek the answer. What is 3,000? I don't know what happened. So you say it's 700.
No, sorry. Okay, this was a good question, right?
Oh yeah.
Easy question, I think.
I don't think so.
What do you mean?
Like it's not easy.
It's
But if I can remember the formula, so. And actually, I think because I understand the question,
That's most important.
so I draw the beautiful picture.
Oh, wonderful.
So it's like two speaker and and actually I used the other formula like sine.
Yeah, the sine one, yeah. That's fine too. No, it's fine.
Because, the n, I mean, I is misunderstand to the x.
What did you make the n?
I make the x equal n. So I think the question want us to calculate the ends. So, but
No, it
actually
doesn't.
n is 1, 2, 3.
Yeah. Yes. But it's okay now, yeah? Okay, how was question 5?
The first one I see is
Is okay?
4 marks.
Yeah?
So I write.
Oh, wonderful. In a nuclear reactor. Read what you wrote.
Oh,
Now go on.
when the reactants mass bigger than critical mass, there are enough free neutrons to continue the friction process and produce the chain reaction. And control rods are used in nuclear reactor to control the friction rail of unreal like U2, 3.
Yeah. Uranium, yeah.
Uranium and plutonium.
Plutonium.
They are composed of chemical elements such as boron,
Silver?
silver.
Yeah. Good.
What? I don't know the two that they are
Composite?
compatible.
Huh?
Like CAPABLE.
Capable.
Capable of absorbing many neutrons without fissioning, then silver, like SELVES. ELVES. Self. Then self. It's then self. I think.
Okay.
Sorry. Yes. And in nuclear engineering, a neutron modulator is a
Medium?
medium that reduces the speed of fast neutrons, thereby turning them into their
Therefore, turning them into thermal
neutrons.
capable, yeah.
Of sustaining a nuclear chain reaction involving U235 or similar fission nuclear. Yeah.
Beautiful. So if you just write that in the exam, you'll get full marks.
No, you too bad.
Too many words, huh? Too many words.
So can I just cancel something?
Yeah. So let me try and shrink it for you. Explain how a constant rate of fission can be maintained in a reactor with reference to control rods and the moderator. Okay, so
The first class I said.
I think I'll start first with the moderator. So I'll say the moderator, like heavy water, slows down the neutrons to allow fission. Further control is possible via the control rod, which covers the fuel rods at different levels. Thus, either increasing or decreasing the fission rate. So let me see, where would my 4 marks go? The moderator slows down the neutrons, that's 1 mark. Further control is possible via the control rod, is another mark. Which covers the fuel rods at different levels, that's another mark I'd say. Thus either increasing or decreasing the fission rate, that's 4 marks. Okay. Oh, I should say what the control rods are made of. I think, what do we say, boron? Yeah, or silver? Yeah. Okay. Good. Okay, let's see, next now. What is the mass that's lost? Okay, so.
Is the reactant minus the...
Yeah, the reactant minus the product.
Yes.
No, wait, this is the reactant. This is the product. I'm confused.
The left side is the reactant.
Reactant product.
Yeah.
Yes, reactant minus product, yeah. So you have this answer?
Yes.
What did you get?
3.202 times 10 minus 28.
Good. Okay. And the energy, you use this formula?
Yes.
And what did you get?
2.88 times 10 minus 11. But I think it's small.
Huh?
It's so small.
No, it's not. It's really not. Because think about it. This is 10 to the minus 28 and this is 10 to the 11. That's 10 to the 17 times more. It's like if I said 1 gram made, or 1 kilogram made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 joules. Do you know what I'm saying? It's not actually very small. It's actually very big. Compared to this. Yeah. Okay. How many moles? Okay, so.
It's 500 over 239.
And what did you get?
2.1.
2.1 moles. Okay, fine. And then.
Finally, I think it is 2.1 times the.
Correct, yeah. 2.1 times 6.02 times 10 to the minus 11 times the energy. What did you get for that? Now that should be a big number.
No.
No?
Because I can.
Did you forget about the Avogadro?
Avogadro is 6. Is 1.602.
Here, Avogadro.
6.02.
Isn't it? Look, Ben. Look. Moles, Avogadro, energy. Multiply.
Is big number?
Oh, sorry. No. 10 to the 11, isn't it? Wait, what's up? No. Sorry. Avogadro is 10 to the 23. 23. So sorry. My goodness, 23.
Actually, I don't think it's because I don't know where's my nose, but just I can still the answer.
What answer?
I just tend just
10 to the minus.
I do 10 to the 2.1. Like I think one more.
1 mole, 1 energy. Did you forget this?
Yeah, I forgot.
You forgot this. Yeah, that's important. Right, do you want to recalculate?
Yes. Well, I searched after Avogadro.
You actually searched Avogadro's number,
Yeah,
and you
I-
forgot to use it.
Yes.
That's gas. That's so funny.
It's 6.02.
Yeah.
Because I remember many cases at 1.602.
There's a few. Yeah. So what's this?
3.64 times 13.
Okay. So do you remember this one, Ben, on the graph? You have to mark in where it is fission and fusion.
Yes, like 15 voice error.
So here, what did we say this was? Iron, wasn't it?
Yeah.
And this is the binding energy, and this is the number, the mass number, isn't it? So we said
Left side.
fusion here, isn't it?
Yeah. And fiction.
Fine.
Just draw this picture.
Yeah. Oh, but now explain why.
Where? Oh, the second. Oh, I skipped this question.
Yeah, I bet. Explain why.
Why?
So, yeah, good question. Why?
No, it's different. It's kind of with
Yeah.
reference to bonding energy per.
Yeah. So the question is, explain why this half is fusion and this half is fission. Yeah. So let's start with the fission. Why do we say the fission is on the right? So the isotopes to the right of iron are big and have decreasing binding energy. Therefore, they're easier to split. The isotopes to the left of iron are smaller and have decreasing. This is if you're moving to the left, and this is if you're moving to the right. are smaller and have decreasing binding energy. Therefore, they're easier to stick together. So, just one sec, Ben. If I go back to this picture, these ones here are the easiest for fusion because they have the smallest energy and the smallest mass. And these ones would be like hydrogen and helium and lithium. Whereas these ones here, they're the easiest for fission. They're the biggest ones. They would be like plutonium and uranium. Okay, what are you going to ask me?
Just a sec.
Sure.
Oh, it's mine.
Okay. Continue.
Okay.
Whoops. If plutonium does not undergo fission, it does not undergo fission, it will undergo alpha decay. What's the decay constant? Okay.
I only find like half-line formula just
Yeah, so you have
C equals a log 2 over lambda.
Yeah. So lambda is log 2 over t.
Yeah. T is
Which
two
is-
seconds.
You should use seconds, it's better.
So
Yeah.
this I just give you answer is 9.35 10 minus 13. 13.
Oh, 30.
No, that's 1 second, sorry.
Okay,
I just thinking is 13 or 13.
oh, right, no, 13. Okay, fine. And then what's the activity?
That is, the unit is BQ.
For this decay oh, sorry. I was thinking this was wavelength. So it's not that. It's per seconds.
Oh, can I describe BQ?
No, it's not BQ.
I think it's.
No, it's similar, but it's not BQ. It's not BQ.
I say
The next one is BQ.
Okay.
So activity equals lambda n, which equals lambda number of moles times Avogadro's number, which is 9.35 times 10 to the minus 13 times 500, isn't it? Yeah, over 239 times 6.02 times 10 to the 23. Did you do that?
Yeah.
What you get?
1.18 times 10 to 12.
Now it's BQ.
But I see the formula is minus lambda.
Yeah, I suppose you're right, Ben. I should really put the minus in here, or I should at least say here decay.
Oh. Means.
Yeah, losing. Yeah. I think that was a very good question. Do you understand now why I say always do the atoms question? Always do the atoms question in the exam. I think it's the best question. Yeah. Don't you think so? Okay, look, I know the first part wasn't nice, all the English. But the rest was very nice, you know? So, this is my advice. I say you should always do the question with the atoms. You should always do the question with the graph.
You mean we choose atom will be
Yeah.
I think so.
Yes, good. And I think, if possible, I like the material question.
Yeah.
So let me look. So for this exam, I would say you should do question 5, because that's the atoms question.
But some, materials, sometimes they ask like a string or.
Yeah, that's okay. Young's modulus is okay. Yeah. Look. Atoms is number 5, okay? And the graph question here is number... Where is it? There. Here's the graph question. That's number 1. Now, in this exam, the material is the same as the graph question. So instead, I think mechanics or electricity, which is easier. This electricity question is okay.
I don't like electricity.
You don't like electricity. And how was the mechanics? Was there mechanics? Fields. Yeah. Never do fields.
Why?
It's students do really badly on it. Really badly. I'm not joking.
No,
Like,
I think so.
yeah. Like this is normal, Ben. Like, for example, you might have a student who would get 16 out of 20, 18 out of 20, and then if they try the fields question, they'll get 9 out of 20. I'm not joking. This is normal. Yeah.
I know. I think so.
Yeah. Do you like waves or not?
Actually, it's the very easy one, but I don't think it's what. I can't believe the question is
This easy.
yeah.
Yeah. So if you don't like materials, you could do waves.
Because sometimes I think my note is some problem, like some definition I lose missing.
Waves has a bit of English in it.
Oh yeah.
The question with the least English, I think, is electricity. The question with the most English is probably waves. Yeah. So, what we'll do next is maths. Yeah? The next exam.
Oh, he's a nice exam.
Didn't we finish it last time?
I don't know.
I thought we did. Let me check.
Maybe yes. Yeah.
I kind of think we did.
We do the math very quick.
Yeah, we did this. Oh yeah, because none of you remembered this. We did it in this room, on this board, with the marker.
I don't have the notes. I don't know why.
Yeah. Why don't you have notes?
It's so strange. What?
Very strange.